net positive suction net, and then we looked into how we were going to do the multi-staging in the pumps. Now, today we will look into the tutorials. So we'll try to solve one or two numericals. So let me take this first numerical. The blade angles at the inlet and outlet of a impeller of a centrifugal pump are 55 and 75 degrees. That is your beta 1 and beta 2. And the corresponding diameters are 3 centimeters and 6 centimeters respectively. The blade width at the outlet is 0.75 centimeter and the speed is around 1500 rpm. The entry of water is radial without any whirl component. What is the meaning of it actually? My VW1 at the inlet is equal to 0. The flow component of the velocity remains constant in the impeller. That is my VF1 and VF2 both are same. Draw the velocity triangles and calculate. First one is the specific work, the flow rate, that is the discharge, then the power required to drive the machine, and then the last one is the manometric head. So these are the four quantities which we are supposed to find, and they are given the manometric or hydraulic or manometric efficiency or hydraulic efficiency, which you can take it as around 0.85. So let's try to solve this numerical. Okay. So solution, let us write the what is given, data. Okay. So the beta 1 is the inlet blade angle, which is 55 degrees. The exit blade angle is 75 degrees, and your inlet diameter is 3 centimeters, means it is 0.03 meters, and the exit diameter is 6 centimeters, means it is 0.06 meters. And the exit width, actually the blade of the width at the exit is, that is B2, we call it as B2 or W2, whatever you want. It's around 0.75 centimeters, that is I can call it as 0.0075 meters, and the speed is found to be around 1500 rpm. Okay. Then, so as the fluid is entering radially, that is with VW1 is equal to 0, I can call alpha 1 is equal to 90 degrees with my VW1 is equal to 0. Okay. My flow components are same, that is VF1 is equal to VF2, which is VF. And the hydraulic efficiency, I can take it as 0.85. Okay. Now what we are supposed to do? We are supposed to find one by one 4 quantities. The first one is the specific work, that is W by M, and the second quantity is my discharge. The third quantity is the power, and the fourth quantity is the manometric head. So these are the quantities which we are supposed to find. So the first and the foremost thing what we'll do is we'll try to draw the velocity triangles. Fine. So now I do have the outer diameter, something like this. This is my outer diameter and this is my inner diameter. I'll try to put the blade. Okay, the blade is something like this. Okay, and I'm going to draw the velocity triangle for this. So this is my inlet VR1. Okay, this is my VR1 as the fluid is entering with radially. So this is my alpha, this is my VF1, which is also equal to V1, and then this is my, okay, this is my U1, VW1 is equal to 0. Okay, this is my inlet triangle, inlet velocity triangle. This is my alpha 1, this is my beta 1. So I am able to construct the velocity triangle. As I told, this U1 is rotating clockwise, so the rotation will be in the clockwise. This is what the sign convention I use. So all my power absorbing devices will be rotating clockwise, and so because of the increase in the pressure, I'm going to the pressure head is developed as the fluid moves out. So with that convention, what we have discussed earlier, I'm going to do with the same convention. Now let us try to draw the exit triangle. So now this goes with the exit triangle. So if I try to draw this, So this is my blade. Okay. So I'll draw my exit triangle. So this is my the relative velocity at the exit VR2, and I do have the absolute velocity which will be in this direction. This is my V2, and I'm going to cover it with my close it with my this is my U2. So this is my U2 velocity triangle, and I have two components of for V2. So one being the flow component. This will be my flow component, which is VF2, and I have my VW2. So this will be my VW2. This is my component of world velocity at the exit. This is VW2. So now I'm able to draw all my the components of velocities. Let me mark the beta angle, that is beta 2. This is my exit blade angle, and this is my alpha 2, which is my flow angle. So if I try to call this as x, okay, if I call this as x, I can write x is equal to u2 minus pw2. So I'm going to keep that as a component of x, because when I try to solve the some of the parameters in the numericals, I'll take that as because that will be the reference for my when I try to use the trigonometric relations. Now, so let us try to solve it actually. So one by one. See, peripheral velocity. See, peripheral velocities are u1 and u2. So u1 is equal to, the formula is pi d1 n by 60. So if I substitute, it is pi into 0.03 into 1500 divided by 60. If I try to enter everything in my calculator, I am getting around 2.35 meters per second. Okay. Similarly, my exit velocity, that is peripheral velocity at the outlet, that is u2 is equal to pi into 0.06 into 1500 divided by 60, which is almost u2 is 2 times your u1, that is 4.71 meters per second is what I am getting. See, these are peripheral velocities or peripheral velocities, or sometimes they call it as the blade velocity. Now let us consider the inlet velocity triangle. So this is my inlet velocity triangle. Inlet velocity triangle. Let us try to apply the trigonometric principle here. Tan beta 1 is equal to Vf1 divided by your u1. Okay. Tan beta 1 is equal to, either Vf1 is also equal to V1. Either I can put V1 or Vf1 divided by u1. Okay. Let me consider from the inlet velocity triangle, from the inlet velocity triangle, okay, tan beta 1 is equal to Vf1 divided by u1. So I need to calculate the Vf1. So if I do a little bit of cross multiplication, Vf1 is equal to u1 tan beta 1. So tan beta 1 they are given it as 55, and u1 just now we found it is 2.35. Let me substitute it. So Vf1 is equal to 2.35 into tan 55. If I substitute, I am getting my Vf1 is equal to 3.36 meters per second. Okay. Now, so in the problem statement they are given Vf1 is equal to Vf2 is also equal to, that is, it's a common, that is Vf, which is also equal to V1, which is 3.36 meters per second. Okay. Now this is the thing what they are given. Now consider the outlet velocity triangle. Okay. If I try to go to the outlet velocity triangle, what I'm supposed to do? If I go and look into my outlet velocity triangle, see, if you take the if I use the trigonometric principles, tan beta 2 is equal to your Vf2 divided by x. Okay, Vf2 divided by x. What is your x actually? X is, okay, x is your U2 minus VW2. Okay. So from there, what is my known quantity? I know the value of VF1, which is also equal to VF2. I know the value of U2, which is just now I calculated. So I can calculate the whole velocity at the exit, which is your VW2. So I can find the VW2 from the exit velocity triangle. So let me go and write that, and let me try to calculate that. So from the outlet or exit velocity triangle, from the exit velocity triangle, tan beta 2 is equal to your Vf or Vf2 divided by your x. Okay, that is your tan theta 2 is equal to Vf2 divided by U2 minus Vw2. Okay, now I will take a little bit of cross multiplication, that is U2 minus Vw2 is equal to Vf2 divided by tan beta 2. So here I need to find only VW2. So I will take VW2, I will take it to the right hand side, so that this will become, so I want to calculate VW2. So this will be VW2 is equal to U2 minus Vf2 divided by tan beta 2. So I will substitute all the values. So U2 is 4.71. Vf1 is equal to Vf2, that is 3.36 divided by your beta 2 is given in the numerical as 75 degrees. So I will substitute everything in my calculator. So if I do that, I am getting the value of your VW2 as 3.8 meters per second. So I got my VW2. So now let us try to calculate one by one. What is the first thing we are supposed to calculate? Your specific work. Specific work, which is W by M. So we know from the Euler equation, this is the formula what we have derived already, VW2 into U2 minus VW1 into U1. As my VW1 is equal to 0, I am left with only VW2 into U2. So let us substitute it. VW2 is just now we calculated, it is 3.8 into U2 is 4.71. So if I try to calculate from the calculator, I am getting my specific work as 17.95 Newton meter per kg or joules per kg. Okay. Next, the second parameter is I need to calculate the discharge. Okay. So discharge. So discharge is given by your flow area. See, look at this. This is the formula. Flow area, that is AF1 into velocity of the flow, or which is also equal to flow area at the exit and your velocity of the flow at the exit. So what is your AF1? So AF1 is equal to your pi D1 B1. Okay, that is my A1, area of the flow area at the inlet, and area of the flow at the exit is actually pi D2 V2. So this is the area of the flow at the inlet and exit. I want to substitute this area. So what is the discharge in that case? This will be pi D1 B1 Vf1, which is equal to pi D2 V2 into Vf2. See, if I will take the second quantity, because D2 is given in the numerical, B2 is given in the numerical, and Vf2 we have calculated. So it will be easy for me to calculate the discharge using the second equation. So I will substitute. So Q is equal to pi into your D2 is 0.06, that is 6 centimeter, 0.06 meters into 0.0075, okay, into Vf2, just now we found it is as 3.36. My Q is found to be around, it's a very small value, it is 4.75 into 10 to the power of 3 meter cube per second. Okay, this is the Q value. Now what is the other quantity I need to find? It is the power. The power required to, so the power required to run your pump actually. So the power P is what actually? Your mass flow rate into your specific work. So specific work just now we have found it is 17.95, but I don't know the mass flow rate. So what is your mass flow rate? Mass flow rate is nothing but your density, that is rho AV, that is mass flow density into your discharge. See, what is the fluid actually? The fluid is water. So rho is equal to 1000 kg per meter cube. This is for water. Okay. Now Q just now you found is 4.75 10 to the power of minus 3. I will substitute this and I will try to get the value of mass flow rate. So mass flow rate is equal to 1000 into 4.75 into 10 to the power of minus 3. So your mass flow rate is equal to, I am getting around 4.75 kg per second. So this I am going to substitute here. So this quantity I will try to substitute here. So if I substitute, my power will be 4.75 into 17.95 joules per kg. So this will become joules per second. So it will be in watts. If I put into my calculator, I am getting 85.4 joules per second or watts. So third quantity also we found. So what is the last quantity we are supposed to find? Last quantity is your hydraulic efficiency. Hydraulic efficiency, which is your eta h by d. What is it actually? Already we have seen, I think in discussion, we have seen the hydraulic efficiency or manometric efficiency is the ratio of your manometric head to your Euler head. Okay. Now I need to find the manometric. So hydraulic efficiency is given as 0.85. So I need to find the manometric. So this I can write it as your manometric head is equal to your hydraulic efficiency into your Euler head. What is your Euler head? Your specific work divided by G. So if I try to substitute the formula for this, like this will be your hydraulic efficiency into VW2 into U2 minus VW1 into U1 divided by G. In your VW1 is equal to 0 because it's a radial inlet flow and there is no world velocity. So this formula will reduce to your hydraulic efficiency into VW2 into U2 by G. So this is your Euler head. So let us substitute it. So this is 0.85 into, so VW2 is around 3.8 into your U2 is 4.71 divided by 9.81. If I do, I am going to get my manometric head as 1.56 meters. See, all the parameters we have found. The manometric head, which is 1.56 meters, the power, which is 85.4 watts, discharge, which is 4.75 into 10 to the power of minus 3 meter cube per second, and your specific work, which is 17.95 joules per kg. Okay, all the quantities, so these are the 4 parameters which we are supposed to find. All the 4 parameters we are able to find. So specific work, discharge, the power required to drive the centrifugal pump, and your manometric head. Fine. So if there are any doubts, so I can take up a discussion. Any doubts?
No, sir.
Fine, super. So you're able to understand. I've gone in detail, step by step I have done. So you can just, I'm going to share the video. You can just go through it again, and maybe you can solve some more problems. Okay, shall I move to the next problem? I'll try to solve one more. Okay.
Yes, sir.
I have shared the tutorials on the Google Classroom. You can download that, and I'll be taking up the second numerical. Okay. The second numerical is something like this. A centrifugal pump, okay, a centrifugal pump is driven by an induction motor at 960 rpm. The flow rate of the water is 50 liters per second. See, deliberately I have given this discharge in liters per second. I want you people to convert it to meter cube per second. See, 1 liters per second is equal to 1 into 10 to the power of minus 3 meter cube per second. Just multiply by 10 to the power of minus 3 or divided by 1000. If you do that, you will be getting in meter cube per second. So I want you people to convert that. That's why I given in liters per second. So against so the flow rate of water is 50 liters per second against a head of 10 meters. See, whenever they try to give the working head of any centrifugal pump, it is your manometric head. Okay. Then the flow velocity is constant at 6.5 meters per second. Okay, 6.5 meters per second. Through the impeller, the blades are radial at the outlet and the losses are estimated as 15% of the output. What do you mean by 15% of the output? What are the losses actually? So if you look at the losses, this means that my hydraulic efficiency is 85%. So the hydraulic losses is 15% of it. So then what is your efficiency? It is 85% or 0.85. That's the meaning of it. Assume the water enters the rotor at maybe once again alpha 1 is equal to 19. That means it's a radial input with VW1 is equal to 0. So what are the things which you are supposed to find here? First thing, the tip diameter of the impeller, that is your outer diameter. That is, if I call 1 as the inlet, 2 as the outlet, so I need to find the D2 or tip diameter. Width of the blades at the outlet, that is your B2 or W2, whatever you want, sign convention. Then fluid delivery angle. Fluid delivery angle means it's the fluid angle, that is your alpha 2. Then maybe the last two one is power required, that is power, and the last one is your specific speed. So these are the 5 quantities which we are supposed to find from this solving this numerical. Okay. Now let us try to solve this numerical. Solution. What is given? Okay. So first thing is they are given the speed which is 960 RPM. Then the manometric head, they are given it as 10 meters. So they are given the discharge as 50 liters per second. That is 50 into 10 to the power of minus 3 meter cube per second. Okay. Then they are given the flow velocity which is 6.5. So VF1 and VF2 both are same. So that's why it is VF I taken. Then there are 15% of losses. So your hydraulic efficiency is equal to 1 minus 0.15. That means it is 85% or 0.85. Then the blade exit angle, that is your beta 2 is 90 degrees. Okay. So the blades are radial at the outlet. Okay, it is 90 degrees. Then your alpha 1 is equal to 90 degrees, and that means your VW1 is equal to 0. So if I try to draw the velocity triangle for this, I will be getting 2 right angled triangles, one at the inlet, one at the outlet, and both will be exactly opposite. Okay. Then let us try to put it what we are supposed to find. To find the first quantity, it is your exit diameter, that is D2, then the exit width, that is B2, then your fluid delivery angle, that is alpha 2, then your power, then the last one is your specific speed. These are the 5 quantities which we are supposed to find. Now let us try to draw the velocity triangle first, then we'll try to solve it. Okay. So this is my exit radius, or this is my inlet radius. Let us try to put the triangle. So this will be my blade. Okay. Then let us try to draw the inlet velocity triangle. So this will be my VR1. Okay. This is my radial inlet. So this will be my, if I try to close it, this will be my U1. So this is my U1. This is my V1 is equal to VF1 because my whirl velocity at the inlet is 0. This is my alpha 1 which is 90 degrees, and this is my beta 1. Now at the exit, I am trying to get a a triangle which is exactly radial. So my beta, see beta toward the exit is 90 degrees. This is like this. So this will be my, so this is my VR2, which is also equal to VF2, and then this is my V2. So if I try to draw your triangle, so this is my U2, which is also equal to VF, sir, VW2. It's also equal to your tangential velocities, VW2, and this is my beta 2, which is 90, and this is my alpha 2. And the rotation is in this direction. So I got my both my velocity triangles at the inlet and exit. Okay. Now let us try to solve one by one. Okay. Now, see, I need to find the different parameters. Okay, I need to find U2, U1, U, all those things and all. So I can find U2 using your hydraulic efficiency formula. See, what is your hydraulic efficiency? We know that the hydraulic efficiency is given by, to this formula. The hydraulic efficiency is equal to your manometric head divided by your Euler head. Okay. Then what is your Euler head actually? Euler head is equal to manometric efficiency, manometric head divided by your hydraulic efficiency. So they have given the manometric head as 10 meters and hydraulic efficiency as 0.85. So I'll be able to calculate my Euler head, that is 10 by 0.85. I am getting from the calculator as 11.76 meters. Okay. Now, what is HE? See, we have found. So, from the Euler equation, from the Euler's equation for the pump, from the Euler's equation, what is HE? HE is equal to VW2 into U2 minus VW1 into U1 divided by G. Here VW1 is equal to 0. I am left with VW2 into U2 by G. Now look at the exit velocity triangle. See, this is my exit velocity triangle. In the exit velocity triangle, your VW2 is equal to 0. Okay. From the exit velocity triangle, okay, I have VW2 is equal to U2. So therefore, your Euler head will become either U2 square by G or VW2 square by G. Either of the type you can put. Either I can put U2 square by G or VW2 square by G. Now I'll substitute this value. So what is your HE? Which is 11.76 is equal to U2 square, as I am supposed U2 square divided by 9.81. So I'm going to take a little bit of cross multiplication, and then U2 is equal to 11.76 into 9.81 square root of it. If I do that, so it's equal to 11.76 into 9.81. If I take a square root of it, I am getting my U2 as 10.74 meters per second. I got my U2. What is your U2? But U2 is equal to pi d2 n by 6. U2 is equal to 60 into U2 divided by pi into n. So I'll substitute all the values. 60 into 10.74 divided by pi into your 50. If I substitute everything, I am getting my D2 as 0.21 meters. So this is the first parameter. So I need to find the exit diameter or the diameter at the exit, which is D2, which is 0.21. Now what other thing I need to find? I need to find the width actually. So we know the discharge. See, second one is I need to find the width at the exit, width at exit, which is D2. It's supposed to find. So we know discharge is given by Q is equal to, so pi D2 B2 into VF2, which is also equal to pi D1 B1 into VF1. So I'll be taking the first one and try to calculate your B2. Okay. Now, if I try to calculate your B, how do you actually? So I'm going to discharge. So discharge is 50 into 10 to the power of minus 3. So 50 into 10 to the power of minus 3 is equal to pi into, so your diameter is given as 0.21, which is just now we calculated. B2 is I'm supposed to find. B2 into your V, they are given as 6.5. Calculate my B2. So B2 is found to be 0.011 meter. Okay, so this is how you can calculate your width. So what is the third quantity we are supposed to find? The third quantity, I need to find your alpha. Okay, what is your alpha? Alpha at the exit. See, the alpha at the exit is what I am supposed to find. So if you want to find that, what I need to do, I will be able to go to the exit velocity. Look at this. The exit velocity, if you look at it, I will take, we will apply your trigonometric principles. Tan alpha 2 is equal to your opposite side, which is VR2 or VF2 divided by your U2. Okay. Now, I know the value of VF2. I know the value of, just now I calculated the value of U2. I will substitute for this, take tan inverse of it, I will be getting my alpha 2. Okay. So that's what I'm going to do here. So from the exit velocity triangle, from the exit velocity triangle, I know my tan alpha 2 is equal to VR2 divided by U2, which is also equal to VF2 or whatever divided by U2. Okay. Then alpha 2 is equal to tan inverse of, okay, tan inverse of VF2 divided by U2. I am going to substitute it. That is alpha 2 is equal to tan inverse of your VF2 is given in the numerical as 6.5 and we have calculated U2 as 10.74. So if I substitute, I am getting my alpha 2 as 31.18 degrees. Okay. Now what is the fourth quantity we are supposed to find? The power required. So that is the power P is given by mass flow rate into your, what is that, work done, or your what we call it as Euler head. Okay, it's also equal to your W by M specific work. Okay, or I have another option. What is your W by M? So W by M is equal to your VW2 into U2. So VW2 into U2 or U2 square. So I can, if what is your mass flow rate? Mass flow rate is equal to, once again, see, mass flow rate is equal to rho into Q. Okay, what is the rho value? Rho is equal to 1000 for the water, 1000 into what is your discharge? It is 50 into 10 to the power of minus 3. So 50 into 10 to the power of minus 3. I am getting my mass flow rate as 50 kg per second. Okay. Now power is equal to, this is 50. What is W by M? W by M just is U2 square by G. So U2 square, see, actually this is your Euler head actually. So Euler it is U2 square by G. But Euler energy is only U2 square because VW2 into U2. So I can write it as U2. So U2 square. So your W by M will be only simply, this will be mass flow rate into U2 square. So what is the value of U2? Actually it is 10.74 square. If I substitute, I am getting my power as 5.77 kilowatt. 5.77 kilowatts. So this is the power available at the rotor. This is the power available at the rotor. Okay. Now the last quantity. So the last one is I need to find the specific speed of the pump. So that is your NSP, which is given by N root Q by H to the power of, that is manometric head to the power of. See here, don't ever substitute your Euler head. You have to see this should be head under which the pump works. That is your manometric head. It's always you have to substitute. So this is 960 into 50 into 10 to the power of minus 3. Okay, then divided by 10 to the power of 3 by 4. I am getting my specific speed as 38.17 RPM. So this is the specific speed. Okay, I'm trying to calculate everything. Specific speed, the power developed, power required, then your alpha, that is flow angle at the exit, then your width of the pump and the diameter. So each and every quantity we are able to calculate what we are supposed to solve from the numerator.